Okay, here we are. We started in advance because we finished earlier so that we can finish a bit before for lunch. We have more time for lunch. So let me start where I finished yesterday. Let me remind you that we were talking about the glassy phenomenology with a particular focus on Moe coupling theory. I was about to finish to show you the basic equation of Moe coupling theory. This was just for me to show you how the theory works. Of course, there would be no time to make all the calculation to have all the equations, but there for me to show you the most important part of the formulas of the theory. And if you're interested, of course, you can read the book of Wolfgang Goetze, or at least a part, or there are many other reviews that are written that maybe summarize it. So if you're interested, I can give you more information. Okay, so we were looking at these equations, starting from Langevin equation, introducing a retarded memory kernel, having in mind that we want to calculate the density-density correlation function in direct and the two reciprocal spaces. We started with solving the equation in principle exact with the approximation that was, I think, the last transparency that I was showing yesterday, the approximation that Moe coupling theory does. So, first of all, we substitute the random force with a projection on a subspace. And then we separate M of t in short times and long times. The separation of the time scale has to do with the fact that we have this Gaussian initial ballistic motion, and then we have a slow rearrangement of the cage. So we have a fast variable and slow variable. This is the basic of this idea. And as you see, the memory kernel can be factorized with two modes from the Moe coupling theory, and a vertex which contains only static structure factor. So this is another important thing of this theory. Since it is a cage theory, it has only the trapping, the transient time in which the particle is trapped is the additional feature with respect to the Brownian motion. And to introduce a transient trapping, I only need to know how far are my first neighbors. So I only need to know an information about the static, okay? So in order to have this dynamical information, I only need the static. I only need the S of k. If I have the S of k, I plug it into a Moe coupling equation, and I get the intermediate scattering function right, okay? The S of k could be calculated analytically for our sphere, for example, and then in fact I'll show you the results for our sphere where the S of k is calculated and plugged in Moe coupling theory equations, or could be measured in experiment and then interpolated with a curve and then numerically inserted in the equation. So this is how M of kt looks like for these two modes. And what is important is that doing an expansion idea close to the Moe coupling singularity, which is the point in which we have the ergodic to non-ergodic transition due to the freezing of the cage, so without topping, so this apparent freezing in real glasses. So, but this is the point in which Moe coupling predicts the arrested phase. So we have an ergodic phase, and then all cages freeze, and we have an arrested phase. We can do an expansion, so Goetze did an expansion close to this critical point in order to have some asymptotic behavior for the correlator in order to cope with the experiments and to give some analytic response, okay? Because S of k, plug it into the equation, doesn't give you anything analytical. But with this ideal equation, they predict an arrested phase, and then they predict some rules that the asymptotic expansion predicts some rules that the f of q at t has to obey. Okay, so this is how the order parameter behaves. This is typical order parameter from ergodic to non-ergodic. And this is the f of qt that will start developing from, do you remember f of qt? We, in the Brownian regime, had to be Gaussian and then exponential with a relaxation time, simple exponential with a relaxation time tau. When you start supercooling, you start developing the cage, and the exponential becomes stretched. The stretched exponential is also known as Rausch-William-Watts exponent. And when you arrive to the transition, you see, you don't decay any longer. The particle is forever trapped in the cage, forever. And this is. Please note, you will see it in the next, that this is a logarithmic scale. So glass transition phenomenon is one of the few phenomena in physics where the relaxation law stretches many order of magnitudes in time. So you will be seeing this correlator always plotted in a linear for the y, but for the x logarithmic scale, so log linear scale, because we are stretching order of magnitudes. And with molecular dynamics simulation, we are able only to follow few of them. The glass transition, close to the glass transition, are stretched like 13 order of magnitudes, which is a lot in physics in general. So, in the MCT, the vertices, as I told you, are only function of the structure factor, and one of the simplest model able to reproduce the phenomenology of the glasses is this called F12, when you have two vertices. Okay, here and in the preceding slide, you saw this Q0, and in the previous one you saw Q max. Okay, so since this is a cage theory, the most clear information on the correlator, on the phenomena related to the cage, is the one in which you calculated f of qt at the peak of the structure factor, because the first peak of the structure factor corresponds to the length of the cage, the radius. So it's like I told you, it's always, when you tune Q in an experiment, the wave vector, you decide where you want to focus your view of the sample, okay? So if you do it at the peak of the structure factor, this plateau will be roughly around 0.7 here, and you will be seeing the decaying due to the cage effect at best. When you go to too small value of R, so high Q, you will be trapped in the cage. When you go too long, you will see a very slow decaying. I will show you also how this correlator behaves as a function of Q. Okay, so we will see several things. Okay, so at finite times, done the asymptotic expansion, our correlator that for us is f of qt substantially, will be equal to a critical value plus a function of t on t over t epsilon, where this t epsilon is t0 and epsilon is T minus Tc divided by T, elevated to 1/2 A. So epsilon is x. X is the variable that is becoming critical. So typically it's the temperature. Could be also the density, but for water is only the temperature. So it's T minus Tc divided Tc. And the T0 is a characteristic time of the particular system that we are analyzing. And what we found is that we can divide the f of qt into the regimes. We have the beta regime, which is when we enter into the plateau, and when we have the alpha regime, that is when we go out from the plateau. So we have early beta, beta, early alpha, which is overlapping with alpha, and alpha. Okay. So Mokablin predicts a power law that you can measure for the shape of this correlator in getting into the plateau, and a power law in getting outside the plateau. The power laws have exponent. I call the exponent of this part A, the exponent of this part B. These are two exponents of the theory that you, if you have the f of qt, have to measure with the fit. Okay, so what the theory predicts is that this G, which is related to phi, as you can see, is a constant T over T epsilon to the minus A entering in the plateau, and minus B T over T epsilon to the B going out of the plateau. So entering is this, going out is this. Fc is the height of the plateau. So you can measure these two numbers. Normal liquid, let me recall you, as a Debye relaxation. So Fs of Qt in the part in which is not Gaussian any longer, not ballistic any longer, goes as F exponential of minus T over tau. When you are supercooled, Fs of Qt for a long time, so again, avoiding the initial Gaussian, will be f of q, which is the 8 of this plateau, this 8, and exponential of minus t over tau to the beta. This law, the stretched exponential, is also called the Kohlrausch-William-Watts law, from Kohlrausch and William and Watts, who introduced for first time the stretched exponential function. And the tau that you extracted here, the Mokablin predicts that goes like 1 over d, where d is the diffusion coefficient that you get from the mean square displacement. So the mean square displacement goes like 6 dt in 3 dimensions. So once you have it and you arrive to the asymptotic part, then you get the d from that with the fit. So you can take tau from the fit, d of the self-intermediate scattering function, d from the fit of the mean square deviation displacement, and both should give you the same gamma. We will see in a while that hopping process will spoil a bit this prediction, because this prediction is correct if we do not have hopping. If we have hopping, it's not correct any longer. Okay, in real simple liquid, Tc, as I told you, is only a crossover temperature because of hopping, and we will see that in detail. Okay, so Mokablin theory, let me show you again the picture that I was drawing yesterday just to repeat the concepts, is a cage theory. So the particle, this is the MSD, and this is the self. The particle, remember that this is the second moment of G over T, so these G over T, F self, S of Q, omega are describing all the same dynamics. So let's compare here. Ballistic, ballistic. So ballistic is T squared. The mean square displacement, do you remember? Went like T squared. We did it in the Brownian model. And at the beginning, and then the F self, correspondingly, the F self of Qt goes down as a Gaussian. And then the particle feels the potential of the first neighbor and start rattling in the cage, and the mean square displacement has a plateau with an height. And the F self of Qt also, so this is the probability, so F self of Qt is related to the probability that I started at t equal to 0, and then I'm decorrelating. So you see the particle is decorrelating by itself, but when it's in the cage, the degree of correlation doesn't change any longer because she's always there. So the degree of correlation remains constant until the cage relaxes, the particle hops somewhere else, and then the correlator decays to 0. Please remember that this is a logarithm, and remember that in order to see two linear laws for the Brownian and for the ballistic, this with slope 2, this with slope 6 dt, you need to plot the mean square displacement in log-log scale, okay? Log-log, log-lin, okay? So this is the t of A entering here, and this is the t, you get the t to the minus 8 entering here, you get t to the b going out, and then here you can fit to the stretched exponential, get a tau, and from tau you can get alpha. Mock-coupling predicts that A, B, and from tau you get gamma, okay? Tau was t minus tc to the gamma. So mock-coupling predicts that A, B, and gamma that you get from the behavior of tau with the fit to the stretched exponential are follow this relation. 1 over 2a plus 1 over 2b is equal to gamma. And A must be between 0 and 0.395, and B must be between 0 and 1. These are the prediction of the asymptotic development of the theory close to the singularity, close to Tc, for T close and higher than Tc. So when you're getting close to Tc enough, how close depends on the system, you start having this prediction that you can test when you do molecular dynamic simulation. What you can do, because mock-coupling theory, you can decide to work in two ways. The first, you get the S of k, and then you plug it into the mock-coupling theory equation, and you get from there the f of qt, or S of k omega, whatever you want. This is one possibility. The other possibility is that you run molecular dynamic simulation, or you measure in an experiment the density correlator, and then you do this fit, you do a test of the theory with matching this exponent, and then I will show you there's another test, which is the von Schweidler test. Then you know that the theory works, okay? Because you calculated the correlator or measured the correlator, and then you just test in the theory through its prediction, okay? So let's do again, let's look again at the F self of Qt. So the particle starts ballistic, then is trapped. When the cage relaxes, the particle is Brownian. Okay. The order parameter is F, which is the 8 of this plateau, and goes like Tc minus T, square root, and let's recall the F of Qt as a ballistic regime at the very beginning. Then it starts decorrelating Gaussianly. Then it goes to plateau. And then at low T, it decays. This region here, entering and staying in the plateau, is called the beta relaxation. This other region here is called the alpha relaxation, and it was named many, many years before mock-coupling, because it was, this is the famous slow decay observed in a supercooled liquid undergoing a gas transition already mid-20th century, okay? Was already called the alpha relaxation. So we have here a microscopic regime. For IT, it's an exponential. For low T, you get the plateau and the stretched exponential. Okay. Let me spend some time, you will come back to that, to this overshoot here. This is what we call in our field the boson peak. Is a quantity that is still under debate what it is, but it's a sort of phonon-like or solid-like behavior, oscillation of the liquids, local oscillation of the liquids that start when you cool down the liquid. And it's a collective phenomenon, but as you might remember, I told you that in the self, which is the dynamic of the single particle, even though you have a collective phenomena and you should see it better in the coherent part, you can see it also in the self. Because if I am oscillating, because a wave is passing through me, then in the correlation with myself, I will see a correlation, an extra correlation, because a wave is passing through me. So I am diffusing, trapping in the cage, etc. Plus I have also an oscillation because of this phonon-like behavior, okay? And then this produces this little overshoot here in the f of qt. You will see the overshoot that you see there, that we show there, in results of the simulations. So for the single particle, we have, let me recap again, A, B, stretched exponential t over tau to the beta, so also beta, and then this relation and this relation. If you calculate the f of qt for a single q, if you do it not as a function of q, but at a constant q, then it's better to do it at the peak of the structure factor, where all these relationships are better calculated because you are focusing exactly on the cage. For t lower than Tc, we have the parameters that are going to zero. So we have this f of q, as I already shown, as this behavior. The f of q is, you can measure it with the neutron scattering, is what you've heard this morning is called the Debye-Waller factor, but I must say that usually neutronists, when you use the self part, call it the Lamb-Mossbauer factor. It's always that factor, but it's for the self. So you have, so this is the Lamb-Mossbauer factor, for example, and it's supposed to behave in this way. And we have, the theory defines a small parameter, which is this one, and then it's the small, and then from here, from the fit here, for t greater than Tc, you can extract this lambda, which is a parameter of the system. And lambda has to be between 1/2 and 1. Lambda is the exponent parameter, and the lambda is related to A and B as one, and there is also a relation, as you can see, between A and B that has to be tested. And gamma is the Eulero gamma function, Eulero in English, I think, gamma function. Gamma 1 minus A to square divided by gamma 1 minus 2A, and the same for B with the plus, and they have to be equal, and both should give you the same result, the same gamma. So you've seen that with the shape of the correlator, I can calculate all these exponents, and then I can fit them, and I can see if they agree with what the theory predicts. So what am I expecting? This is a density correlator calculated for the hard sphere system. In this case, this is not a result of a simulation, but this is the result of plugging in the S of k that for hard sphere can be calculated inside the Moog coupling theory equations. If you do this, then you have this stretched exponential behavior that comes out of the correlator. And then when you arrive at the structural arrest temperature and you lose ergodicity, you have, as you can see, the plateau. And then, in this case, for hard sphere, you are changing the packing fraction. And then, if you keep on increasing it, the height becomes higher and higher. Let me show you how, so the Moog coupling theory was originally formulated and never at the beginning was not calculated anything with the molecular dynamics simulation. The first, there were only results from experiments that were indicating, I will show you through the susceptibility, that A, B value could be calculated, they were fitted with the theory, but the tests were less precise. And Cobb and Anderson, as I was telling you yesterday, did the first test, which was a test done using a Lennard-Jones potential, which is this, that is a repulsive core and an attractive part. And these are the value of sigma and of epsilon. So sigma is here, and epsilon is this is the how do you call that? The minimum of the potential. And in order for this mixture not to crystallize, first they had to use the mixture, and second they had to change these numbers, not using the usual average that we do when we want to calculate the interaction between A and B particle. We usually do the mathematical average here and the geometrical average for these two. And these are Lorentz-Berthelot mixing rules. Instead, they didn't use the Lorentz-Berthelot mixing rule. Not only that, so sigma AB is even smaller than sigma BB, so the closest distance where BB can get is larger than the closest distance that A and B can get, and the equilibrium position when A and B, when you're sitting on A, for example, and interact with B, it's more stable when they are mixed than when they are interacting with themselves. This gives a boost not to crystallize and to remain mixed, also not to separate. So these results were published in a Physical Review Letter and 2 Physical Review in 1995. This is a snapshot of the Lennard-Jones binary mixture, A particle and B particle. As you can see, are different in radius and in strength of the Lennard-Jones system. And let's see the results. This is the S of Q, S of K. Q is always the wave vector. We call it the K until yesterday, but it's a wave vector. So this is the correlation of A particle. This is the usual S of K. You have seen others during the other lectures. This is internal unit. Lennard-Jones usually is given in internal unit. And these are the time of the simulations. So this is the mean square displacement. So this is the first one that I show you calculated in a simulation. As you can see, at high t equal to 5.0, you have log-log scale here. You have ballistic, and then you see the slope changes, and then it's proportional to t. So t square and t. You see that it's a t squared because 1 decade here corresponds to 2 decades here, and 1 corresponds to 1 when you go to t, so you can see it also with your eyes. And when you supercool, you start developing the plateau. And the plateau is a signature of the cage. Okay, now let's look at the cage again for the Van Hove self-correlation function. I can see exactly that there is a caging in Van Hove self-correlation function if I look it at as a function of different time. So let's look at a high temperature where we still do not have the caging, and at a low temperature where we have the caging, okay? So at high temperature, do you remember that we saw with the Brownian regime that the self-intermediate scattering function has to be a Gaussian? Do you remember that? Okay. And of course, the probability, as the time gets longer and longer, of that me, who started to move at r equal to 0 and time equal to 0, have explored a certain distance around the place where I started, is distributed on larger and larger space as time progresses, okay? But if we are in a normal regime, we will see a fast decay as time progresses of this Gaussian when it's ballistic. Then it becomes slower, and it's Brownian, and it's always moving and getting larger, moving and getting larger, okay? When we go to a very low temperature, when the mean square displacement shows the plateau, so we know that there is a cage, this is what happens. At the beginning, you have the ballistic time. So this is the probability distribution. So see, 4 pi r g self is the density of distribution of probability. And as you see here, this is for low time that is fastly going down because this is the ballistic part. But when it fills the potential cage, you see the curves are very similar to each other. So when you are rattling in the cage, there are several times, the times in which the particle is trapped in the cage, in which G, the Van Hove self-correlation function, doesn't decay. It's always the same. Sorry, it's always the same. So the particle explores always the same space, even if you are seeing it at longer and longer time. Then the cage is relaxed, and the particle is free to move. Okay? And then the behavior becomes more similar to that one. Okay. So, correspondingly, as we have seen, we have the f of qt, and let's look at the f of qt for both particles. This is for a particle at q equals 0.7. The 8 is a bit high. I don't remember if it's the first peak of the structure factor. Let's go back and see it. Yes. So it's at 0.7. It's at the first peak of the structure factor, Q7.25. And these are high temperature, these are low temperature. As you see, it beautifully fits the prediction of Mach coupling. B particle is similar. So there is another test of the theory that you can do. The theory predicts that there is the time-temperature superposition principle. If you fit the tau, each tau at each temperature, and you plot all the curves dividing the time of each curve by tau, where tau is the tau of that temperature, so you do it for each curve, this curve follow a master curve here for a limited amount of time, which is this one. Okay, this is, the theory predicts, in fact, if you do this, T over tau, that the phi of Q is universal. The universal is a master, universal for that particular fluid, and it's equal to F of Q minus H, a constant, T over tau to the B. So you extracted the B from the going down of the curves, but you can fit the B also here from this part. And most importantly, if Mock coupling holds, you must see that all these curves follow a master curve, okay? You must see the master curve. This is another test of the theory. This is always at the peak of the structure factor. In the meantime, you can make a fit to the Rausch-William-Watts with the later part of the Q curve, and you will find a value for beta, which is not a B. Beta is the exponent of the stretched exponential. Okay. So MCT, as I was telling you, has a range of validity. First of all, when you start from high temperature, at the beginning you start seeing developing the plateau, but the cage is not well formed. And you have to see with your data what is the moment in which Mock coupling starts to be valid. Because the asymptotic expansion in principle is very close to TC, but as a matter of fact, is far enough that you can test it. Okay, so both at low and high temperature, you have deviation. The deviation at high temperature are due to the fact that the cage is still not completely formed. The deviation at low temperature are due to the fact that you have hopping. And this, still for Kobe-Anderson, is testing also the prediction that D should go like tau to the -1, so it should be fitted with a power law. You see the linear part is a power law with gamma. But you see that there is a difference between D, there is a slight difference between D and tau here for this mixture that is due to the fact that, for example, there are hopping effects. This is the coherent Debye-Waller factor that you can calculate out of the theory for A, AB, and BB. So the Lambos-Bauer factor or the Debye-Waller factor, they look different. In the case of the Lambos-Bauer factor, it's very similar to the S of K. In the case of AA and BB. For AB, of course, it's a mix of the correlator shown. In the case of the Lambos-Bauer factor, you will see we will show the comparison, a decaying function. Okay, let's see what happens as a function of Q. Do you remember that I told you that best way to see the caging is to use the first peak of the structure factor for the calculation of the self-intermediate scattering function as a function of T. Here is what I was telling you about what is happening to the correlator as Q get larger or, larger or smaller. When Q gets larger, it means that you go out of the cage. You don't see very well the going out of the cage. And in fact, this plateau is going down, and eventually, if it's very, very large, it disappears. You will see only the ballistic part, because you're not following out of the cage. You're using only very small length scale to see the phenomenon. And as you enlarge it, it's exactly the contrary. You are seeing the relaxation over longer and longer time scale, like in a magnifying glass. So this is low Q, and this is IQ for the I particles, okay? So that was the self and the coherent. Another thing that I wanted to show you here is the difference between the self and the coherent. So this you see, for example, this one is the coherent and this is the self. The coherent, you have more this oscillation that are the signature of the correlations between the particle. This here is the self-intermediate scattering function as a function of Q. which is the thing that I was telling you. By looking at different lengths, you see slightly different correlation between the particles. This is a comparison between substantially the Lammers-Bauer factor and the Debye-Waller factor. So the Lammers-Bauer factor is the one, sorry, the Debye-Waller factor, so the one related to the coherent scattering is this wavy function here, calculated in two different ways. Don't mind the two curves, almost similar curves. And very similar to this dashed curve, which is the S of Q. While the Lammers-Bauer factor, which is the one connected to the incoherent part, is decaying. Is the plateau, this is a function of Q, is decaying, as you have seen in the previous. So this plateau is decaying as Q increases, as you've seen in this previous slide. Very well. Sorry, let me see. Okay. And so this is the exponent of the Monschweidler law for the coherent and incoherent part. Again, the exponent, the Monschweidler for the coherent is the more continuous decaying function. The Monschweidler for the incoherent reflects the correlation of particles, and it's more wavy. This is a comparison of B as gotten from the Monschweidler exponent for the A particles, and from the stretching, and compared also with the exponent of the stretched exponential of the beta part for the A particle and for the B particle. So these are the comparisons. So B is slightly different from the stretching exponent, and though they have a similar trend. Another important thing I wanted to talk to you about when you inquire on Moe coupling theory and possible test is the frequency domain. Of course, if you're running molecular dynamic simulation, you calculate the f of qt directly, because it's a sum of exponential. While if you want to calculate the s of qt, you have to do the Fourier transform. So usually we calculate the f of qt or the g over t, which also we calculate directly. S of k and omega has to be calculated with a Fourier transform. When you do experiment, very often you get the S of qt. So in many spectroscopy, so information is in the frequency domain. So they measure, generally speaking, the real part of the response function or the imaginary part of the response function, which is called dynamic successibility, or they are linked to the dynamic successibility. For example, the S of k and omega is related to the imaginary part of the dynamic successibility in this way. And also the polarizability that is measured in light scattering is a dynamical response function related to the dynamical successibility. In general, so the total successibility is this one. So when you look at this chi, for which we can, of course, calculate out of molecular dynamic simulation, and for example, Cobbe-Anderson calculated it for their mixture. So you see how they behave. And again, since S of qt is the Fourier transform of f of qt, you can get A and B also from this frequency domain. And you get them from the behavior here and here, okay? So this time you have A on this side and B on this side. So when you plot the chi, you see you have these two coming out and coming in the plateau. Coming in, coming out. This is now frequency, so omega. So they are inverted with respect to time. So this is a slow time, this is fast. So Gaussian ballistic is here, and here is low dynamics. This is also a problem in neutron scattering, when I told you that the alpha relaxation time is stretching many order of magnitude. but in frequency is going to low frequency. So this becomes a problem of resolution. So if you want to measure, for example, the alpha relaxation with neutron scattering, you should do quasi-elastic neutron scattering. So you look only at the low frequency, long times. And also you should apply for an instrument who has a very high resolution. The higher, the slower the time that you can measure, okay? So this is important always when I was telling you that when we have to make a project, we have to think very carefully what is the range of temperatures, but also the range of time and space, or in the frequency domain, in the K domain, that we want to measure. So you see the alpha relaxation is going very fast here, so where we have the place where we have the limit of resolution, for example, for neutron scattering. But a neutron scattering experimentalist can measure B, and A, which is not exactly A, is an effect A because of the problem of the boson peak that affects this area, with this formula, where this x is a time, A multiplied by omega over omega minimum A effective plus B time. So you can do this fit of this small part here, and you get A and minus B. And you can use this as two parameters of the theory, so also from experiment and also from simulation. If you want to prove the time temperature superposition principle, you can do it also in the omega frequency by dividing by omega max. And as you see, all the curve collapse in the low frequency, the alpha relaxation curves, collapse in a master curve, as you see for this part very well. And then, of course, when you get out of the window, you have some deviation. Okay, so MCT parameters that the Coben-Anderson extracted from D and from tau, for example. So from D, T minus TC minus gamma, they got this TC, very similar also from tau, for a particle, Rho C, which is the critical density also, because with Mach coupling, if you are doing monoatomic fluid, density and temperature are similar, and they found these two. And then gamma, 2.35 and 2.85. If we look at B, same temperature, because see, Mach coupling predicts that these exponents should be the same for both A and B particle. So if you have a mixture, this mixture is undergoing the glass transition, then the parameters have to be the same for both the species, cannot be different. And in fact, the test is quite good because you see that the values are very similar here between A and B particle. It's only that we have a deviation of gamma from D and from tau, and the reason is hopping. So you see, when you calculate D is calculated at extremely long times. So there is a phenomenon I didn't mention to you, but that you can imagine, or maybe I said that, but let me tell you again. When the cage starts to freeze, so we are in the deep supercooled region, even if it's not frozen, the particle can get, while it stays trapped, an activation energy to jump. So there is an intermediate time region in which the liquid is both relaxing because of cage relaxation and relaxing because of hopping. It's doing both things. So in that region, you will see deviation between the gamma that you extract from D a very long time. So if the time is very long, it's very likely that the particle had this activation energy because it's a matter of probability. And from tau, where the time is much smaller, and so this is more asymptotic gamma, and this is the gamma at the tau. So this gamma here has no hopping, and this gamma here has more hopping, and so you see difference. Apart from that, the prediction that the A and B value are similar is respected. How about the von-Schweidler law? So the one extracted by the master curve, we have Fc, which is this equal to A and B, HQ, which was the constant multiplying the exponent, and exponential decay. And then B, as you see, is quite similar between these two. Similar enough. Okay. How about MCT critical exponents and what kind of lambda we get? This is from the von Schweidler, lambda 82 for A and 0.77 for B. From D we get 0.7 and 0.60. You see hopping hits very badly, and deviates from the theory. But from tau, very similar to von Schweidler. So taking into account that we have the hopping, the theory, the test is working well. So remember the expression between A and B, and also the gamma that leads you to lambda. From this expression, we calculate this table. And no, sorry, this was Coben-Anderson. I say this because I will show you that we did some calculation for a confined mixture. MCT parameters and critical exponent, therefore, can be summarized in this table. From von Schweidler, we get this value. From D, this value. From tau, this value. Now, I don't want to go through all of them, but the take-home message is that where we see deviation is because of hopping. Let me show you also the experiments now. This was an experiment in 1996 done on potassium cyanide, KCN, and you can see exactly the behavior that Mock coupling predict when you calculate this is the light scattering. This is the Lammos-Bauer, the Debye-Waller factor. When you calculate the Debye-Waller factor, you see exactly the experiment that took into account this behavior predicted by Mock coupling. When you look below MCT, this, for example, is a deviation calculated with the simulation on the B kappa S potential for silicon. You see that this is the Mock coupling behavior, and when you start having hopping, if you supercool very much, you start having a strong deviation and the Arrhenius behavior due to the activated process. But we will come back to that point when we look at the water result. Now, I wanted also to tell you something else. You remember that I promised that I would talk about what happens when you start having hopping. So the potential energy landscape and the inner structure formalism introduced by Stilling and Weber is what permits you to understand the physics below the Mock coupling crossover temperature. What are inner structure? Are configuration of local minima of the potential energy landscape. So this is a bit misleading as a picture. It's a cartoon because this is a one-dimensional representation of many variables, okay? I collapsed all these variables in only one, but you must understand that these are several kind of minima and maxima, and so they have orders, they can be classified. It's a many-dimensional, multidimensional space. And this is the potential energy. This is what I was telling you about several times. The deepest minimum is the crystal. And then we have the glass and transitional states. So when you get stuck here, if you write to the ideal glass, you write to the ideal glass transition. If you get stuck here, you might see aging, because in this region you can see some phenomena of aging. And you start from an equilibrated configuration, and then you quench the system. And you can use, for example, the conjugate gradient minimization method that will take you to the ideal glass. In the short time regime, you make a motion around the minima, and a long time regime gives you, for hopping processes, the transition between basins. So this is what happens when you have hopping processes. Down I brought something that Goldstein brought, but let me go on, because otherwise I run out of time. And now, when we switch from Moog coupling behavior to hopping, we have in liquid what is called a fragile to strong transition. This transition, you see it in tau, in the behavior of tau. The tau you calculated from the stretched exponential. The exponential is always stretched, also when you have hopping. When you have hopping, your F self of Qt will show a stretched exponential. You will see no difference in the FF of Qt. It's becoming longer and longer, it's stretched. But when you take the tau and you fit it, you can fit it to Moog coupling theory or to the Vogel-Fulker-Tamman expression, which is this one. This is a phenomenological expression that they use, still use, but is phenomenological, and it dates back to when the alpha relaxation was first discovered, in the mid-past century. The experimentalists introduced this phenomenological formula. This is Moog coupling theory formula, but when this is valid, also this is valid. So you have to decide what kind of a number do you want to extract out of this. This is a slightly larger range of validity, but they are equivalent. It's fragile. With this behavior, so we distinguish between fragile and strong glasses. So some glasses are only fragile, some glasses are only strong. Some glasses, most of them are fragile, of the simple liquid, are fragile at the beginning, and then they turn to strong. Okay? So fragile is when you have cage relaxation, strong is when you have hopping, and tau behaves as a typical activated process with an activation energy, which is this one that you can measure when you fit to the behavior of tau, and the activation energy is exactly the fluctuation that you need to overcome the basin where you were trapped. Okay? So another important thing is this. We showed that the Moog coupling theory is good for water, and I showed it together with Xiaoxin Chen, Francesco Sciortino, and Piero Tartaglia back in '96. After the paper of Kohber-Andersen, we saw that paper and we decided to do the test for water. And it is important, since water is a molecule, that we don't get confused with rotations. In all my talk, there is nothing about rotation. Rotation is all another story, meaning that you have also a rotational correlation function, okay? Rotational correlation function. So how is the rotation that I do at a certain point correlated with the rotation that I do in another point in time-space? You can do a full analysis of both of them, or you can only concentrate on translational dynamics. So in the case of water, center of mass. So the results that I will show you for water are center of mass. We did back in 1996. Also, I personally wanted to do it, so we did it. I show an evaluation on how rotation and translation were coupled, okay? And I showed that the rotation and translation decouple when the cage relaxes. So we can talk about translation, and then rotation is another story. Okay? And this is another important issue related to the fact that I told you that you always have to know what a cross-section measures. For example, NMR measures rotation. So if you want to compare to neutron scattering, when you measure translation, you cannot compare, because that correlation could be different. Could be due to rotation, so to other phenomena that we are not analyzing here. Because physics is complicated. When fluid become more complicated, physics become even more complicated. So it's important for you to stick to the simple facts, to the simple things, and then to add the complications. So add the rotation, add other correlations, okay? And remember that this part here is present in many simple liquids. In the simple liquid, usually it's like this. Okay, so we will talk about translational dynamics, okay? So now, before I pass to talk to you to water, let me just make a brief, comment on confined liquids. You have other things on confined liquid you're hearing here in these seminars. But let me just talk about the confinement respect to this kind of dynamics. Of course, confined liquids are very important for technological and biophysical properties. And when you supercool a confined liquid, there are changes in dynamical and thermodynamical properties. Of course, molecular dynamics help us to get a full access. And we could see whether, and we started also, I did it over the whole career, to see to what extent the Mock coupling theory was still valid in confinement. So, and how the glass transition scenario transferred from bulk to confined phase. So, as a model, we did a model of this Lennard-Jones binary mixture confined in an array of soft spheres. So the red ones are soft spheres, and the yellow and the blue are the A and B particles, or the B yellow and A blue particles of the Lennard-Jones binary mixture. So remember that the ratio between A and B is 800A and 200B for the Cobb and Anderson Lennard-Jones binary mixture. We published the results in a set of papers back in the days, 2003, 2 in 2003, 2 in 2005, and a last one in 2009. And I'm going to go fast on these results because it's a comparison with the bulk. But this was just to show you the confinement. This is the confining system. These are a representation of equipotential surface of disordered matrix of soft sphere. And it's a nanoporous amorphous material, like could be Silica aerogels. So it resembles reality. So we are studying, as you can see, a liquid in a strongly confined environment. And we're gonna, since we are using Cobb and Anderson binary mixture, we will compare with their results. And sorry that I don't understand why this is out, but it's written parameters. I will correct that before preparing the PDF for you. Parameters of the potentials. So this is the potential, these are the parameters. Is Cobb and Anderson and the soft sphere. But let me go fast. This is thermodynamics, it's not interesting. This is the radial distribution function that we calculated for the bulk and in confinement. But let me go, this is the static structure factor. Let me go to the R square. So you see the bulk on the top, the confined at the down. As you can see that they are similar, but the confined it looks a bit different. And in particular, the B particles behave a bit differently. But now, since we want to talk about water more, I don't want to go too much into the details of the comparison between confined bulk. The take-home message that's also in confinement for the system, Mock coupling theory works. There are some differences, of course, because the confining space is introducing different, but not so important if we think about the testing of Mock coupling theory. There is one difference, though, that we analyzed in detail, which is the hopping. There is more hopping in confinement. Hopping can be clearly seen, and this was the other message I wanted to give you before passing to water, can be clearly seen in the Van Hove self-correlation function. While in the f of qt, I told you that when you have hopping, you always see a stretched exponential, and then you have to go and see tau. When you measure the self-intermediate scattering function, you see hopping because instead of this Gaussian or Gaussian-like behavior, you start seeing other bumps. You will see them in a while. And then you know that there is hopping because the particle is jumping. And then this, in this correlation function, show a shoulder or a bump. For water is a shoulder, for this little particle, you really see the bump. So here it is. You see this bump here? This is always the probability for pi r squared G self. So this is the Gaussian decaying, almost Gaussian because it's hopping, makes some deviation. But most importantly, you see this peak here? And so this is where this peak here we have two peaks. And as you can see, this is an hopping phenomenon. I have a better picture, which is this one. Okay, this is more beautiful. Can you see the hopping? So we have the main peak that is related to the trapping in the cage. So it's still here, very localized, because we are going down in temperature now. So the particle is always trapped in the cage, but can hop. And it can hop only for a very long time. You see, as soon as you get longer and longer the time, this is T, this T here is very, very long for this simulation. You see that is hopping. And this is one hopping to a position, because this is R, and this is hopping to a further position. So this is our A particle, and look at B particle. The B particle for this time, see A particle for this long time, still has an alpha relaxation. The B particle for this long time is only made of hopping practically, you see? All this wavy behavior. So when you want to see if there is hopping, and because you see sometimes when you look at the fit between more coupling and fragile to strong, sometimes some not expert in the field say, why can't you fit everything with only one law? First of all, no, because coupling is diverging. So if you have 3 points like this, it's out of question that you can into this point because it's diverging. So it's also a lack of knowledge of functions. But apart of that, if you calculate this, then there is no other objection that can be done. Your fit could be done in a different way. No, here, without the benefit of any doubt, the particle is hopping, okay? So if you do this kind of study, remember, if you want to make it sealed, also for the referee, you calculate this, and there is no more story, okay? Hopping does exist. The cage relaxation does exist, because we see also that part of the Van Hove correlation function that is not moving. You increase time, and it's always the same when it's in the cage. So you see the phenomenology in this correlator. Did you understand? This is an important part. Was I clear enough? Are you following? Okay. Okay, this is nice because Gustavo also was talking about the non-Gaussian parameter. Non-Gaussian parameter is something that is used also when we talk about hopping, coupling, etc., because it evaluates the degree of non-Gaussianity of the Van Hove self-correlation function, and is defined. There are various non-Gaussian parameters depending on, I said alpha, I should have said n, sorry, here is n. So we did the calculation for n equal to 2, but you can calculate also 3, 4, and evaluates the degree of non-Gaussianity of the Van Hove self-correlation function. And we see that there is a substantial enhancement of hopping processes for A particle, and so of non-Gaussian parameter with respect to the bulk. Because I forgot to tell you that hopping is increasing for A and B particle when we go to confinement. But It's increasing more for A particles that are larger, and it was more difficult for them to hop in the bulk. They are hopping more, and so hopping is introducing strong degrees of deviation for non-Gaussianity, from Gaussianity. Okay, from the intermediate scattering function, we did also in confinement the fit, and we compared the parameters. We got results compatible with the bulk, with the only difference that, I'm not going through all the details, the only difference is that we have more hopping here, so deviation show up before. This is the Kohlrausch, this is von Schweidler time-temperature superposition that you see works very well for the curves. So we can say that Moog coupling is still valid in confinement. This is another very nice prediction of the theory that we tested, that the B parameter is Q-independent around the peak of the structure factor, and in fact, this is the B parameter extracted from von Schweidler as a function of Q this time, and as you see, is Q-independent around the peak of the structure factor. This is the wave vector analysis as a function of Q, and see here, you arrive practically not to see this. When you have a high Q, you stay inside the cage, you don't see practically the alpha relaxation anymore. These are the parameters that we extracted, the plateau that is behaving the Lammos power factor as I showed you for the bulk, the tau, and the beta. The beta is asymptotically going to B for IQ. This is what the theory predicts, and in fact, we arrived to the value of B that we extracted with the von Schweidler. We did the test, and everything works. Last thing about that I wanted to no, there are two things of theory about the low temperature region, the one in which we have hopping. As also Gustavo was mentioning, we can study cooperative rearranging region. So we can see below a certain temperature if there is a number in which a region a number of particles is correlated and is rearranging, and how these regions are distributed. So two particles belong to the same cluster if they satisfy this rule. So as a function of time, they remain close enough. And this is the difference between confinement and the bulk of the distribution of the cooperative rearranging region as a function of the particle of that belong to the bunch of particles that are doing this together. This is another kind of analysis that can be done when you study the region that is below the range of validity of Moog coupling. Okay, we've done also the study with the growing soft sphere. I don't want to present these results to you. Let me just tell you something more, because for water I've done a similar study, so let's look at it now in general. When you have this potential energy in escape, you can calculate what they are called the inherent structure, that are configuration of local minima in the potential energy in escape. So starting from an equilibrium configuration at a given temperature, the inner structure is determined by quenching the system with the conjugate gradient minimization method. And then you can calculate the canonical partition function that has this expression. So if you want to do what is called an inherent structure analysis, you can calculate the distribution function of inherent structures, and this is the number of distinct basins that have this energy of the inherent structure, and the logarithm of this number multiplied by KB is the famous for us configurational entropy. So the configurational entropy is something that you have to evaluate when you want to calculate the entropy of the system. So you have a free energy vibration inside a single basin that can calculate with the vibrational contribution to the entropy. And in the bulk system, the free energy is inside a single basin harmonic. And is it true also in confinement, the analysis that we do for the bulk, for example? It is, because we did the calculation of the P of the inner structure. These are all the distribution of the several inner structure. It's a function of P. And we did the inner structure analysis also for the confinement, and it came very similar to the bulk. The total entropy can be calculated by thermodynamic integration, and you have S total, which is given by the vibration around the local minima, the configurational entropy, and this is the liquid, and then you have to add a contribution due to confinement, which we calculated in this way by the derivation of the potential due to the confining potential. So we have result of the confined entropy, the total entropy, and the entropy that comes from the liquid bulk contribution. So you can also modify this calculation that usually is done for the bulk for confinement. And let me see, what time is it? Well, I think that I'm thinking, okay, let's do this, and then I just briefly introduce water, and then we stop. The vibrational entropy is obtained. The configurational entropy is obtained as I just described, and if we look at a comparison of the density of state of the bulk and confined, you see that it's rather similar. So this inherent structure analysis, that is an analysis that is usually done in bulk, can be done also in confined. And here I finish the part that I wanted to show you for as a description of all the phenomenology that we will see with water. Let me use this last 10 minutes, a bit more actually, it's 15 minutes that we got, to start talking about water, and then tomorrow we will finish. You've heard a lot already, an hour talk that I did about water. In that talk I was focusing mainly on thermodynamics. So you have seen that water has a rather complex thermodynamics. And but the dynamics is connected to the thermodynamics. So the results that I would like to present to you about water are these. First of all, let's make a brief recap of the thermodynamics of water, which I already described yesterday. And I will talk about this Widom line and the dynamical crossover, because there is a link, as I was saying at the end of my talk yesterday, between the thermodynamics and the dynamics. And we get this link through the fragile to strong transition and the Widom line, that they are very close to each other, practically coincident. And then we will see the MCT in the bulk and some experiments. The MCT in the bulk for SPC, T4P, and T4P 2005. And we will look at the fragile to strong crossover. And if I have time tomorrow, I will talk to you also about the last part of the seminar that I didn't have time to do yesterday, which was the slow dynamics of hydration water close to the surface of a protein. So this is the plan for the rest of the lesson of today and tomorrow. So let me recap that I told you yesterday about the fact that water, is polymorphic and polyamorphic, and the water has this interplaying structure in the liquid. It can stay in a high-density liquid configuration and a low-density liquid configuration. Of course, also in the pentamer, this structure break and reform. Maybe the pentamer is not complete. It's a liquid, but it's a very stable structure. That's why water has this very strong tendency to crystallize because of this strength of this local pentamer. And then you have the high-density liquid and the low-density liquid. The interplay between these two is generating a liquid-liquid critical point in the metastable phase, predicted in simulation with no doubt that doubts about predicting the critical point in the simulation do not exist any longer. As Pablo De Benedetti said the last time, the argument is, the thing is closed. Is for sure existing in simulation. It's a metastable liquid-liquid critical point, very difficult to measure in experiment. But as I told you, they had indirect confirmation through measures of a Widom line and through measure of a first-order phase transition between high-density and low-density liquid below the liquid-liquid critical point. These are the work of the group of Anders Nilsson in Sweden, and are two science papers, 2017 and 2021, if you want to go read them. Okay, so we have this phase diagram. Let me recall it to you. So we have a critical point here, which is the liquid gas and the liquid gas coexistence line, melting line, supercooled water region, no man's land, where the critical point should be, but a Widom line point that it was measured by the group of Anders Nilsson. This critical point is due to the interplay between two structures. So in the one-phase region, we have this Widom line I will talk you about in a while. And here, in the two-phase region, we have a low-density liquid in one side and high-density liquid in the other side. Okay. So this is the chemical review that I brought together with all my friends and colleagues. And this is, again, the phase diagram that I showed yesterday. So remember that we have this particular line that is the line of maximal correlation length that in thermodynamics points to a second-order critical point. This is the liquid gas, and as I told you, I've done a Nature Communication and a JChemFIS together with Mauro and Dario Corradini, which was a former PhD student of mine, that we found experimentally that the peak of the specific heats are pointing to the liquid gas critical point. Because among the other things of the community, at the beginning they were saying, no, this Widom line doesn't exist, there is a study done on Nature, I think, in which they proved that when you want to introduce in a paper, for example, a very good idea, and you have very good result, usually the paper is accepted. If the idea is too ahead, the community refuses it. It's too new, refuses it. So usually the paper is rejected. Not because the referee it's just because the referee, because the mind is closed. They cannot accept, because for years and years, this thing didn't exist. This was proven out of statistics. And so don't get discouraged if your paper is not accepted. As Gene Stanley once in an interview, our longtime friend Gene Stanley once in an interview said, his most important paper, the most cited, was rejected by Nature because the referee said that it was an unimportant derivation of an incomplete derivation of an unimportant result. So bang, bang, just cut this out. This is most cited paper. So you see, you shouldn't trust always the referee. But when things are too ahead, too far viewing, the paper could be rejected because of how a mind works. I mean, the referee is, let's leave the referee that wants to reject your paper because it's your enemy. This is something we are not treating here. This is a spontaneous thing. If it's very new, is refused. Okay, so I was telling you at the beginning, when Gene Stanley, for the first time, introduced again, because the Widom line was known in the theory of critical phenomena, but in Gene Stanley and his co-worker, for the first time, said, look, here, my former boss, Xiaoxin Chen, measured this maxima, and Gene said, okay, I think it's a Widom line. They made the simulation, and they made a PNAS, Xu et al., 2010, I think. It will be cited later on. I'll point it to you. And they showed that there was a Widom line. At the beginning, the community, Widom line, this is an invention, it doesn't exist. But the Widom line, it did always exist, and so it's there, for example, in supercritical water. So we started to make papers, as usual. When the community tried, a small part of the community is saying it's not true, then you have to start making works and showing that beyond the benefit of any doubt, this thing is true. And in fact, for example, if you want to look at my main Nature communication, we found a Widom line, of course, as Gene has already pointed out, for the supercooled liquid, close to this second order critical point. Okay, this is to give you just a little color. So we have another 5 minutes left to go. Let me just introduce you the concept of the Widom line more rigorously, and then we finish for today. Okay, the concept of Widom line was there many years before, but it wasn't called the Widom line. It was Gene Stanley who called it the Widom line. Is considered in the last year in the context of supercooled water, in connection with the possible existence in experiments, because in theory, with simulation it exists, of a liquid-liquid transition terminating in a second critical point. This is the PNAS I was telling you about. This is the first paper in which is introduced the liquid-liquid critical point. For potential that show an LCP, ST2, T4P, T4P 2005, and AGLA, we find also a dynamic crossover, dynamic quantity that crossover upon crossing the Widom line. The fragile to strong crossover for potential that show LLCP happens on crossing the Widom line. And it's also found, we found it also in ionic solution, in confinement, and in a solution of AGLA in Earth sphere. Okay, experimentally, this crossover was measured in confined water and very recently in bulk. So we have, in confined water, this is an experimental paper by Xiaoxin Chen and al. And it's and then we have the physical review letter, and then we have also in bulk water Bruce Kai and his group that made a PNAS in 2016. Okay, and then we found it also in supercritical water. This was the Nature communication that I told you about, and the JCP that we published out for. This contains the experimental values, and T4P 2005 for comparison. This contains several water potential that all show a Widom line, and so they all match with the experiment. And the key metal, as I was telling you recently, found a Widom line in bulk supercooled water inside the no man's land, And let me tell you again that if you find a Widom line, there must be a critical phenomenon close by. So this is an indirect explanation of the existence of a liquid-liquid critical point, experimental. Okay, the Widom line, what is it? In a fluid, when we move from the critical point into the single phase region, you expect the correlation length start showing maxima. These maxima are anticipating the divergence of the correlation length at the critical point. So in this region, since correlation length is diverging, quantities like specific heat, isothermal compressibility show maxima, and these maxima merge on a pseudo-critical single line that terminates at the critical point. And so it means that you can use the specific heat and the isothermal compressibility as proxy for the Widom line. Instead of calculating the correlation line, which is a bit more complicated, you can do it from the SOK, you can also calculate the specific heat. In my nature communication, you will see I calculate them all and they converge, and you see the convergence for supercritical water, also in experiment. So, they collapse because they start to become proportional to the power law of the correlation lengths, and this line to which they all collapse, and so the line of maxima of a Widom line, of a correlation length is the Widom line. Let me tell you that the Widom line is well known, as I was telling you, in supercritical fluids. So there is a paper by the group of, it is a paper by Gorelli et al. My good friend Giancarlo Ruocco is between the authors, and also Tullio Scopigno, who is in La Sapienza, experimentalist that graduated, took the PhD with Giancarlo, and now is professor in La Sapienza, is doing this work, did this work. In the case, this is done for argon, liquid argon, I think. The picture, I think it was, it's argon. And you can see that they, in the case of the liquid-gas transition, what we expect is that the Widom line separates liquid-like from solid-like, liquid-like from gas-like phases. This means that we are still not in the two-phase region, but that this region on the left is more gas-like, and this region on the right is more liquid-like, okay? So, so this is noble gases, argon probably, and someone other. And so they found a Widom line in noble gases with the experiment. And this was done through, actually they found a crossover in the sound velocity, and they connected it to the Widom line, okay? So through sound velocity in experiments, they connected it with the Widom line. What we have done instead, it was to work on supercritical water. Supercritical water, it's important for chemical engineering, carbon capture, storage, pharmaceutics, waste disposal, other areas of application like gasification of biomasses. So, and there are technical difficulties in experiment, because as you might know, when water gets supercritical, it becomes very corrosive, eats all the chamber. You make a beautiful chamber, then you prepare the supercritical water, and supercritical water eats the chamber, melts it, destroys the chamber. So there are technical difficulties. We analyzed the properties of supercritical water in experiments and for TIFF 2005 water, and then in a second paper with other popular water potential. And we found out the Widom line through the study of specific heat isothermal compressibility, but also we found also through the isochords. So when, isobars. When we study the supercritical isobars, and these are the experiments, and the curves who have the same colors, since one is T4P 2005, the other is experiments, are calculated at the same distance from the respective critical values. As you can see, the phenomenology is very, very similar. And we are, so you see the phenomenology of course, of a critical point. And the specific heat maxima from experimental water are like this. So we can plot the specific heat maxima and see where they are pointing. We can also calculate the viscosity. So this is experiments, still experiments, and with the specific heat maxima, we consider it a proxima of the Widom line. And if we look at the experimental viscosity, look at the flexus is exactly at the Widom line. So, the bold line is the viscosity of the dilute gas limit. So this is the experiment, this is the simulation, and again, this is the Widom, this is d to the -1, that is similar to viscosity, and again, this is the Widom line that we extracted from simulation that follows exactly where the flexus is. And here is, for example, what we found out, that thermodynamic and dynamic line all converge of the Widom line for a range of circa 30 Kelvin and 90 bar. So what are these lines? So the black lines are the bulk, the experiment. This is all bulk. And the red line are T4P 2005. Circles, filled circles, are the liquid gas critical point. And then the continuous line are maxima of the constant pressure specific heat. Long dashed line are maxima of the coefficient of thermal expansion. And short dashed line are maximum isothermal compressibility, and squares are crossover from the simulation in D, and the diamonds are crossover from experiment in crossover in dynamics in eta, and crossovers are change of slope of transport coefficient in D and in viscosity. And what we found out is that when we have this dynamic crossover, of course in the supercritical it's not fragile to strong, but this is a dynamic crossover, is because the fluid is passing from a region in which is more gas-like to a region in which is more liquid-like. And of course, dynamics is slightly different. So you see always in the dynamics this signature of the thermodynamics. And so we published these results in the Nature Communication, and then also we did the test with other potential, and we did the other Jake and Fis, but this I'm not going to present you also those results of the Jake and Fis that are similar to this, but it's Nature Communication 2014, Jake and Fis 2015, with the other potential. They are similar results to this one that I am presenting here. Okay, this is all for today. And questions? Yes. Can you speak louder, because I can't hear, because there is this air conditioning. We did it already, we did. Because when you have a small box, for example, you have other wiggles there where you have the boson peak, but these are not the boson peak. These are due to finite sides, okay? So we did several boxes and we saw that the boson peak is not moving with the sides. The other wiggles, yes. So if I think I have the figure. I have one figure in which you can see what are the wiggles due to finite sides and what is the wiggle due to boson peak. Yeah. Exactly. Finite sides, yeah. Thank you. Yeah. It's hard to tell, because I would have said that in confinement it was more difficult to hop, no? Because to hop you need an empty space. In fact, I haven't shown you yet, but I will show you tomorrow, that if you take the G of R, the peak of the self-intermediate factoring function in R of hopping follow exactly on the peak of the G of R, because of course those shells are the most likely in which you can have an empty good space, energetically favorable but empty, where the particle can hop. I would have said that in confinement everything became more close and you had less hopping, but maybe no, maybe it's more difficult. The problem is the other way around. Probably in confinement, structural relaxations, so global rearrangement are more difficult, so cages become frozen more, and still there is room for hopping. These are also small particles, the Lennard-Jones, so easy for them to hop also in confinement. Single particles, not molecule. For example, you will see the hopping for water, but it's a shoulder, not such a nice peak, because for water it's more difficult to find a place to hop, so there's not so many water that hop. Other questions? Okay. Thank you.